When we collect and organize data, we really have three options. We can keep it as an original data set. We can create what's called a frequency table. We can also create a stem leaf display. Each one of these has its own strengths and weaknesses. Some of the points of comparison are going to be details versus data reduction, ability to handle large data sets, and the ability to get what's known as a qualitative sense of center, or what's known as central tendency, and what the distribution is like. So with the original data set, right, we have excellent detail, no data reduction because of course we have every single individual data point. Right, the ability to handle large data sets is cumbersome. It's cumbersome with large sets because if you have 10,000 data points, you got a pretty big set to deal with, and it's also difficult to get a good sense of center and distribution, because you just have so much data sometimes it's hard to know how it all averages out. When we have a frequency table, that has some data reduction. You'll see in a moment when I give you some examples. Easily handles large sets though, so that's its strength, and is better at that sense of central tendency and distribution. The stem leaf plot has excellent detail. There's no data reduction involved with stem leaf plots. Is okay with larger sets, still bad with very large. It still becomes cumbersome, but is actually good at central tendency and distribution, and get a feel for what those are like. So we'll go through and look at each one of these. And of course, And the original data list looks, something like this. Right, and you have your list of numbers, right, and you can do all of your calculations, your central tendencies, calculations of distribution. Of course, this is a relatively small data set. Again, if we had 10,000 data measurements, then this would be a little cumbersome. Now, a frequency table creates what are known as intervals. And we, of course, will have a table. And the headings are intervals and, of course, frequency. And I'll put an example of intervals now. So here are the examples of 6 intervals. Don't have any context for the data, but apparently all the data is going to fall between -10 and 20. Notice how the intervals are broken up. We have, this is x is greater than or equal to -10, so -10 would be in this interval. But this is x is less than -5. So -5 would not be in this interval. It would actually be in the next interval. And that's an important distinction, all the little details, because if you happen to get a value right at the border of an interval, you have to know which one to put it in. And as you collect data, maybe there were 4 numbers that were in this interval. Maybe there were 10 numbers in this interval. Maybe there were 25 numbers in this interval. Maybe 21 numbers in this interval, and then 7, and maybe there weren't any in that interval. So you get a sense of distribution. Like, okay, it looks like it's somewhat symmetric. I would guess the average is going to be somewhere in this range. Now you do have to be a little bit careful. It gets a little confusing sometimes as to what is the data, right? Data values. This column in here are not data values. This is the data value. And so there are 10 numbers between -5 and 0. And so a data value might be -4, -3, another -3, a -2. All that's the data. The number 10 is not the data. So we have to really be careful about that and make that clear. And you can see about what I was talking about with data reduction. Maybe there were 3 -4s and only 1 -3, or maybe it was the reverse. Maybe it was only 1 -4 and 4 -3s. We don't know, because that level of detail has been kind of absorbed into this interval. And so that's what's known as data reduction. We've had a reduction of details. But the benefit is we can have an enormously large data set, and it's very easy to record all of the data in this frequency table. Now, when we talk about stem leaf plots, I think I'm going to need a new page for stem leaf plots. Stem leaf or displays. Stem leaf displays are kind of another way of, they're similar to original data sets. I'm going to put some numbers up. So here's an original data set that I'm going to convert into a stem leaf display. So what we're going to be doing is kind of dividing these numbers up. And you'll notice that I'm going to draw a line right down there. And this becomes my stems, and these are my leaves. And I'm going to organize these in order. And so it looks like my smallest stem is 11 and the biggest one is 17. So I'm going to go 11, 12, and then I'm going to look and say, well, how many 11s do we have? Well, it looks like there's only one, and the leaf is 4. Do we have any 12s? Yep, looks like we got 2 of them, one here and one here. We have 123 and 127, so we have kind of 2 leaves there. Do we have any 13s? Nope, we don't actually, so that one's blank. 14, looks like we have 1. 15, we have 3. 151, 152, and 158. Don't have any 16s, and we have 1 17. So, and this, what we usually do is kind of put what's known as a scale. If we have 15, 2 represents 152. So it's kind of a key so that you can read the stem leaf plot properly. And so it gives you kind of a graphical view of the distribution of the data, which is why it really is helpful to see, you can see the distribution. You can probably get a decent sense of where the center is. It actually would probably be, somewhere around here, around 14, I would guess. Maybe a little bit less, between 13 and 14. You can handle more data because it's kind of a two-dimensional chart, but when you get to really big data sets, you're still going way off the page, and it becomes cumbersome. So you can see that there are certain strengths and weaknesses to each way of showing data, of organizing data, and you choose the one which gives you what you need.